Guys, our planet's dying!
The global average temperature has risen by 0.9 degrees Celsius since the late 19th century.
This may not seem like much, but this has caused the sea level to rise by about 9 inches.
Greenland has lost an average of 286 million tons of ice per year in the last 20 years. The rate of ice mass loss in Antarctica has tripled in the last decade.
The increase of greenhouse gases is not only warming up our planet, but it's also making our oceans more acidic. Since the beginning of the Industrial Revolution, the acidity of the surface of the oceans have increased by 30%.
No one is happy about this. People have been protesting non-stop in an attempt to make a change.
Possible solutions have been proposed. However, some of them are more favorable than others.
In order to reduce greenhouse gas emissions and make David Attenborough proud, we have created the most efficient and easy to manufacture wind turbine in the world, capable of powering not one, not two, but 3 light bulbs.
These light bulbs consume in total 33 watts of power. This is equivalent to the peak power of our turbine. It's not much, but it's enough to read a book, as you see.
Our objective was to create a state-of-the-art wind turbine which would weigh less than 200 grams and should fit in a box with specified dimensions.
We also wanted to achieve maximum power coefficient at a TSR of 2 pi. We will now explain this in detail.
Our objective was to design a wind turbine which would spin clockwise and also weigh less than 200 grams. Albert Betz found out that the maximum power that can be extracted from the wind using a turbine is independent of its design. Betz's law was derived from the principles of conservation of mass and momentum of the airstream flowing through an idealized actuated disk. According to this law, no turbine can capture more than 59.3% of the kinetic energy in the wind. This is known as Betz's coefficient, and it is the CP we aim to achieve. The first step in designing our wind turbine was to decide the TSR, which was calculated using the following equation, where R is a radius, N the number of blades, and S the length of the strongly disturbed air upwind and downwind. The optimum TSR was found to be 2 pi.
The TSR then determines the rotor diameter, as part of the design brief was not to exceed 3000 RPM at maximum power output. Therefore, the rotor diameter has to be chosen in accordance with the equation for angular velocity. As the tip speed is determined by the TSR and the RPM is limited, the radius has to be chosen so that for the required tip speed, the rotational velocity does not exceed 3000 RPM. The next step was to select airfoils for the blade. We chose S8 series airfoils as these are specially designed for wind turbine and have high maximum lift-to-drag ratios. The root of the blade, or the first 4 centimeters, are made of an S833 airfoil, which is thick and is thus able to sustain the stresses that the rest of the blade exerts on the root. From 4 centimeters to 10 centimeters, the blade section gradually transitions to an S803 airfoil by 3 interpolated foils. From 75% S833 to 25% S803, to half and half and 25% S833 and 75% S803. These interpolated airfoils were created and analyzed using Q-blade. The S803 is then used for the remainder of the blade, as it is a thin airfoil with a high maximum lift-to-drag ratio, and at this distance from the hub, the structural loads are reduced, eliminating the requirement for a thicker blade. The next step was calculating the optimal chord length along the blade. This was done using the equation on the board right now, which essentially means that the chord is inversely proportional to the distance from the hub. As shown on the diagram, however, this relation is not used on the first 10% of the blade, as here the chord becomes thinner as you go towards the hub. This is done in order to smoothly attach the blade to the hub. The final step in the aerodynamic design was then to calculate the twist angle at each point along the blade. This was done by finding the angle of attack at the maximum lift-drag ratio for the airfoil using X-foil, calculating the relative wind angle at the given point using simple trigonometry, and then adjusting the twist so that the wind angle matches the optimum angle of attack for that particular airfoil.
One of the challenges of the design process was to ensure the turbine could fit inside a box of 400 by 150 millimeters. As you can see, the blade does not fit inside the box. We were initially inspired by a dog bone hinge mechanism, but we chose to limit the rotation at each end to one direction. In order to get around this, we decided to use a folding mechanism to reduce the effective length. We chose to place a hinge inside the middle of the hub to maintain symmetry, and to not interfere with the aerodynamic and structural calculations. And we made certain that there was sufficient space for the hub to rotate freely without collision.
During our design process, we were inspired by how birds of prey use their wings tips to reduce vortex generation. Incoming flow causes high pressure at the front of the turbine, as opposed to the lower pressure at the back. This difference in pressure causes air to rotate around the wingtips, thus producing a vortex. Using a blade lid, we reduce the pressure difference at the tip, therefore reducing the strength of the vortex produced. These vortices represent energy losses. This causes the overall efficiency of the wind turbine to increase.
As it was explained in the previous section, to maximize the performance of a wind turbine, we need to maximize the lift generated at each point along the blade. However, this can lead to very excessive aerodynamic forces acting on the rotor, especially when it is rotating at 3000 rpm. Hence, carrying out structural analysis is essential to ensure the blade will perform properly and sustain the high level of rotation. In the structural part, three important aspects have been considered: the effect of centrifugal stresses, then the contribution of stresses developed due to bending. Those can be significant, so we had to make sure that the lift generated won't break the thin structure. Finally, the magnitude of deflection was computed, as it can significantly alter the pressure distribution over the blade.
We discretized the blade into 201 airflow sections of uniform thickness, each with unique chord length, twist angle, and airflow type. Over the span of the wing, the type of the airflow changed few times. Thus, to be able to accurately represent the blade, airflow coordinates had to be generated accordingly. Next, we computed the cross-sectional area of each lamina, together with the lift, drag, coefficient data, and the velocities. We obtained the aerodynamic forces experienced by the wing.
Knowing the geometry of the cross-section at each point, we were able to compute the variation of the position of the centroid and the second moment of area along the blade. This allowed us to compute the magnitude of bending moment at each point. The peak stresses develop in the lower surface of the blade, as here the bending and the centrifugal stresses have to be added. The bending stresses can be calculated by the following formula: m over y times y equal to sigma. So we were able to check whether the material will avoid yielding in the lower surface of the blade.
It's important to make sure that the blades do not have too much tip deflection, as this would mean our aerodynamic loads were different than what we calculated, and this would invalidate the entire Q-blade analysis of the rotor. The unit load method has been used to calculate the deflection of the blade at each point. In our initial test, it was seen that the turbine had a slow start, needing a wind speed of 20 meters per second to begin rotation. A bigger twist at the root of the blade would have caused the blade to self-start at lower wind speeds.
We have estimated 10 degrees of tip deflection, which seemed to be accurate.
At 8, 10 and 12 meters per second, a CP of 0.103, 0.147 and 0.161 was achieved. This was achieved at an average TSR of 7.74, which contrasts our predicted TSR of 6.28. However, the maximum CP was achieved at 3,400 RPM. This is above the 3,000 RPM limit.
The CP produced by our turbine did not meet our expectation of 0.25, and neither did our TSR prediction with a 23% error.
These errors could be attributed to the bladelets, which add an element of uncertainty in a critical region of the blade. A more rigorous approach to their implementation may have resulted in a more predictable performance. Use of CFD would have allowed us to estimate the effect of the bladelets on the overall flow distribution of the turbine.
Also, the large mass centered around the nose cone was too large, and this caused the turbine to accelerate too slowly. With a lower mass, a lower lift would have been required to keep the blade in rotation. Lift being used to keep the turbine in rotation could have been used to produce torque and hence increase the power produced.